Hi everyone, today's topic is about slope. This is Unit 1, Day 2. Our objectives are, I will be able to identify the slope of lines, and I will be able to write equations of lines given a point and slope or 2 points. If we follow our unit progressions, the previous lesson was on points, lines, and angles and how to correctly notate them. Today we'll be talking about slope. Moving forward, we'll look at parallel and perpendicular lines, midpoint, distance formula, equation of circles before our Unit 1 assessment. Our statement of inquiry for today is this idea that change is all around us. Things are constantly changing, and being able to quantify or put numbers to that measure of change helps us to better understand the world. Now, an example of that might be, how is the temperature, the annual global temperature, changing around the world? And if we look at this first graph here, let's start by reading the title, Average Annual Global Temperature in Fahrenheit. And it goes from 1880 to 2015. So it's a really, really large span of time. From there, we always look at our axes. How are they being labeled and what is it indicating? This is our y-axis and this is our x-axis. Along our x-axis, you'll be able to see that this is years, starting from our 1880 going all the way to the 2015 mark. Along our y-axis, we can recognize that those are our degrees in Fahrenheit. And you can see it's this really, really large range of values, right? It starts from way down in negative 10 degrees Fahrenheit to 110 degrees, all right? So this will be degrees Fahrenheit. And what you can recognize is that it's this really slight upward trend, but it looks very flat, right? And I want us to take that and then compare it to the second graph that we have on the right here. Again, the title, Average Global Temperature by Year, and says that the data is from NASA, all right? Similarly, if we look at our y-axis and our x-axis, we can see that those are years along the bottom and that these are our degrees Fahrenheit. I want you to take a second, and what is the major difference between these two graphs? One of the big differences is actually the range of our y values, right? The first one went from a negative 10 to 110. And then this one on the right goes from 55 degrees to 60 degrees Fahrenheit. It's a much smaller range of values. And within that smaller range of values, we're able to see these different changes going up and down. Now, we still see that general trend upwards, right? If we were to draw kind of a line of best fit, it is still going upwards, but it tells us more specific information that we don't get from this initial graph, this first one. Now, graphs are a really common way that we can show change mathematically, right? In this instance, you see that temperature is increasing over time. They can also be used deceptively. By understanding slope and how to write an equation, you'll become less susceptible to the deceptive graphs and data. Now, a lot of people who argue that climate change isn't a large problem, it doesn't really affect us that much, or maybe saying that it's not nearly as man-made as some people would argue, would use the graph on the left. You see, like, look at that. You can barely tell, right, that it's increasing. But if you have a very solid understanding of climate and weather and temperature and science, you'd understand that the graph on the right is a more accurate representation. And because of all of these changes, because of this increasing trend upwards, that it is something that we need to be concerned about. So being able to understand how to read graphs, understanding change, writing equations can help us to become less susceptible to deception. So let's start off by understanding what slope is. Now, slope measures the steepness of a line as a ratio. And another way to think about ratio is a fraction of vertical change over horizontal change. And many of you guys might have heard of that as rise over run. How much are you going up and down versus how much are you going to the right? All right. And I'm hoping, fingers crossed, that you guys have learned this equation. Slope equals y2 minus y1 over x2 minus x1 when you're given two coordinate points. All right. A lot of times when we talk about slope, we use the variable m to represent slope. All right. If we look at the right here, Mr. Slope Guy helps us kind of quickly remind us and recognize if we have a positive slope, right? So this guy is positive, and that is a line that is going with a positive slope. If you have a negative slope, we'll have a line that goes downwards from left to right. If we have a slope that goes straight up and down, it is considered undefined, hence the U. And then if you have a 0, like a flat slope, oops, there we go, here, then you have a 0 slope, okay? So you can use those to help us recognize if you look at a line, this is positive, negative, undefined, and 0. Now our first example is looking at this map. All right, you can tell that this is an approximate map. It's not perfect, of some of the major cities in the United States. And in this one, we want to go from Dallas to Boston. So here's Dallas right here, and then Boston's right over here. And it says that we're going to fly directly. So we're going to envision that it's a straight line going that way. And it wants to know what the slope of our trajectory is. So in order to do this, we probably want to start off by figuring out what are the coordinate points of our two cities. So Dallas, we can see it's at 2, -4. And then Boston, right there, is at 7, and that one's an 8. Right, now once I have my two coordinate points, I always like to label them x1, y1, x2, y2. And that helps us when we want to use our slope formula, right? M equals y2 minus y1 over x2 minus x1. I'm just going to plug in those numbers. Our slope equals 8 minus -4. 7 minus 2. Remember, this minus is a part of your equation, so we have to include it when we fill in our x's and our y's. And 8 minus a -4, we know is a positive 12 over 7 minus 2 is 5. So we get a slope. The slope of our trajectory is 12 over 5. Take some time and try this student example on your own. Now I want to introduce 3 common forms that you'll see equations written when we're talking about linear functions, straight lines. All right. The first one is probably the one that you're most familiar with. It's called slope-intercept form, or y equals mx plus b. When we look at y equals mx plus b, the m represents the slope, right? It's the same m that we solved for in our example number 1. And this b represents the y-intercept. Where is it crossing our y-axis? So if we look at our graph right here, this b is 1, so we have that point right there. So it crosses at 1. That's our y-intercept. And then the x and the y describe a specific point, right? So we know that this point's on the graph, this point's on the graph. It explains all the x and y values that would be true along that line. So slope-intercept form is really useful if you know the slope and the y-intercept. But sometimes that's not the information you get. So another common form is called standard form of an equation. And this is our ax plus by equals c, where a, b, and c are constants. That means they're a number, and a is always positive. So if we look at this equation to the right, you have 3x plus 4y equals 5. And you'll see that this x and y here are the same x's and y's in our slope-intercept form. Now the last form of an equation is called point-slope form. This is our y minus y1 equals m times the quantity x minus x1. Now here we have our x's and y's that are the same x's and y's from our standard form and our slope-intercept form. But you'll also see that they have these x1 and y1 with the subscripts. And these are talking about a specific given point, all right? So if you know what a given point is, then you can plug in those x1, y1 values. And then again here, the m is your slope, which is the same as the slope in our slope-intercept form. Now this is a really useful form if you have a coordinate point and the slope. It's easy to plug those values in, and hopefully in the examples coming up, you'll be able to see how we use these different forms. So this next example asks us to convert the equation from standard to slope-intercept form. So it gives us this equation, 3x plus 4y equals 5, and it asks us to convert it into slope-intercept form. So standard form, ax plus by equals c. And that's what we have here in this example. And we want it to become slope-intercept form, y equals mx plus b, where m represents our slope and b represents our y-intercept. What you'll see here is that we are isolating our y. We want to get this y completely by itself. So similar to when we were solving equations in the first lesson, we want to do everything so that we can get y all by itself. So we have to think through that inverse operations, starting by asking, do we have to combine any like terms? There are no like terms here, so we can move on. Is there anything that's being added or subtracted? And in this case, yeah, there is. There's a plus sign right here. Since the 4y is already positive, we can actually keep the 4y on that side. And we want to get rid of the 3x. Since it's a positive 3x, the inverse of a positive 3x is a minus 3x. And 3x minus 3x goes to 0, so it goes away completely. We can cross it out. Our 4y drops down. And then we have negative 3x and a 5. We know those are not like terms, so we can write them negative 3x plus 5. And you'll see that I wrote the negative 3x first because in our slope-intercept form, our x's come before our constants. All right, now we have a 4y, which means y is not alone yet. The 4 and the y, when you have a number and a variable right next to each other, we know that always implies multiplication. So the inverse of multiplication, to get rid of that 4, is division. So we're going to divide everything on the other side by 4. Now 4 divided by 4 is 1, which means we're left with 1y, which is why these crossed out. We are left with 1y equals negative 3/4 x plus 5/4. And now we have an equation in slope-intercept form. So give your example a try, the student example number 2. Now let's take a look at this third teacher example. It says to write an equation given the point, given the slope is negative 5/3 and goes through the point 3, -3. If we see the information that's given to us, we have the slope and we have a point. If we look at our forms of equations, slope-intercept form is useful when we have slope and the y-intercept, but we're not given a y-intercept in this one. Standard form, not really. Point-slope form is useful when we're given a coordinate point and the slope. So this is the form that we're going to want to use because you're given a slope and a point. So if we do y minus y1 equals mx minus x1, where we know that the slope m is negative 5/3, and we know that the point is 3, -3. So this is our x1 and this is our y1. All right, now we have those three values that we're going to plug into this equation. Y minus -3 equals -5/3 x minus 3. We have a minus and negative here, which will turn it into a plus. Y plus 3 equals -5/3 x minus 3. And that's it. That's our equation. So give your your student example a try. Now, teacher example number 4. The civil engineering firm that you work for has just won the rights to develop and build a direct freeway from Dallas to Atlanta. The first thing that needs to be done is to determine the equation of the line of the road that would follow. So we're looking from Dallas going to Atlanta. And it says it's a direct freeway, right? So we're going to think straight line, just like that. Now, in order to find the equation, there's a couple of things that we need to know. We need to know the slope, and we need a point, or we need the y-intercept. All right, here, we actually are given 2 points. We know where Dallas is, and Atlanta is at 5, -7. So we're given 2 points, which is actually really good because we need those 2 points to figure out the slope. So y2 minus y1 over x2 minus x1. Sorry, x1, y1, x2, y2. So if we plug it into that equation, we get -7 minus -4 over 5 minus 2. And we're going to simplify that. We get -3 over 3, which is -1. So we know that our slope here is a -1. Now we have a slope, and we actually have 2 different points that we can use. So we want to use our point-slope equation. Y minus y1 equals mx minus x1. All right, so let's use the Dallas point just since they're already there. Y minus -4 equals -1 x minus 2. Again, we can simplify that negative minus into a plus. So y plus 4 equals negative, and it's a -1, so we can actually just get rid of the 1, x minus 2, just like that. And we have the equation of a line that describes the direct path between Dallas and Atlanta. All right, try this example on your own. Now, I want you to, again, look back at all of the information that we've been through in these couple of pages and think about what are the things that you already knew and what are the new things that you learned this lesson. And I want you to start to synthesize a summary. The summary should be between 3 and 5 sentences. I want you to really consider that statement of inquiry. And I want you to make sure you're using the proper academic vocabulary, specifically the ones that we introduced today. So if we're talking about lines, and are you talking about slope-intercept form? Are you talking about these specific points? Are we talking about the slope? See you next time, you guys. Bye.